Until Voyager arrived in the Neptunian system, this was the least understood of all the planets. Invisible to the naked eye, Neptune was a world hidden from view. Even through the most powerful of telescopes, it appeared as no more than a blurry ball of blue and green. The fourth largest planet in the solar system by volume, and the third largest by mass. From afar, we knew nothing of its atmosphere or its structure, and had only faintly observed two of the moons in its orbit, Triton and Nereid. This was a planet that had remained very firmly in the darkness, a distant world that had clung on tightly to its secrets for over 140 years. Even the discovery of Neptune played out in the darkness. The last of the planets to be discovered, it is the only one whose existence we predicted before it was ever observed by the human eye. For centuries we stared at it without knowing what we were looking at. Almost certainly, Galileo was the first human to peer at Neptune directly, during a series of observations at the end of 1612 and the beginning of 1613. The data he plotted with his newly invented telescope led him to believe this was a fixed star in the night sky, not a planet. Over the next 200 years, many astronomers must have fixed their gaze on this dim star without realizing the significance of its bluish light. But the first hint of its true nature would appear not in an eyepiece, but in a set of astronomical tables. In 1821, the French astronomer Alexis Bouvard published Tables astronomiques, a set of tables predicting the orbits of the three outer planets, Jupiter, Saturn and Uranus, based on Newton's laws of motion and universal gravitation. Over the next few years, Bouvard's theoretical work would be tested against the movements in the night sky, and his painstaking calculations were rewarded with the confirmation that actual observations of the movements of Jupiter and Saturn adhered precisely to his mathematical predictions. However, Uranus refused to behave quite so compliantly. The movement of the then farthest planet deviated substantially from Bouvard's predicted path, and this led him to make a wild suggestion. Either Newton was wrong, or perhaps there was an as-yet undiscovered planet lurking in the darkness, distorting the passage of Uranus through its gravitational interaction. A flurry of astronomers sped to find the hidden planet, the ultimate prize for any stargazer, as an acrimonious race kicked off between the British and French to predict the planet's location. On the British side of the Channel, the Cornish astronomer and mathematician John Couch Adams became obsessed with Bouvard's hypothesis and was convinced he could use nothing more than pen and paper to determine the size, position and orbit of this hidden world. By September 1845, Adams had at least partially completed his calculations, but unknown to him, almost simultaneously, the French mathematician Urbain Le Verrier in Paris was completing his own complex computations of Uranus's path and the elusive eighth planet. By the summer of 1846, Le Verrier had played his hand and announced to the Académie des Sciences on the 31st of August that he had calculated a predicted location for the missing planet. Revealing his work just 2 days before, Adams secretly sent his own prediction in a letter to the Royal Greenwich Observatory for verification. In what must be one of the most close-run races in scientific history, Le Verrier engaged the Berlin Observatory in the search for his planet, and at 00:15 on the night of the 24th of September 1846, Johann Galle, with the help of his assistant Heinrich Darré, looked through his refracting telescope and became the first person to knowingly gaze at the eighth and furthest planet in the solar system. A planet that had taken decades to locate was found in less than an hour, and within 1 degree of the position Le Verrier had calculated. Even today, the exact credit for the discovery of Neptune is still disputed, but in the winner-takes-all world of astronomical discovery, it's Le Verrier whom history records as the discoverer of Neptune, the man who discovered a planet with the point of his pen. It took another 143 years before we would visit Le Verrier's planet and witness a dynamic, violent and volatile world. As Voyager drew closer, it began to return a precious set of images that remain to date our only close-range record of this planetary system. At first flying past Nereid, the third largest of Neptune's moons, Voyager captured our only image of this distant world travelling on its massively eccentric orbit around the planet But it was the images of Neptune itself that became increasingly astounding. Painted across the surface of the planet, Voyager revealed banks of methane clouds that were being whipped around by high-altitude winds at speeds of over 2,000 kilometers per hour. At least 5 times stronger than the most powerful winds ever measured on Earth. These were the highest wind speeds we'd witnessed anywhere in the solar system. It wasn't just violent winds that we saw through Voyager's eyes. Great hurricane-like storms could be seen moving across its surface, the largest being an Earth-sized storm system similar to the Great Red Spot on Jupiter, which became known as the Great Dark Spot. Voyager took multiple images of this vast storm system as it sped past the planet, skimming the cloud tops of the northern pole from a distance of just 4,400 kilometers as it reached its nearest approach on the 25th of August, 1989. No one had expected such massive storms to be brewing so far from the Sun. But just 5 years later, with the Hubble telescope up and running, we peered back towards Neptune and found that the Great Dark Spot had disappeared. Unlike the giant storms on Jupiter, which we've witnessed playing out for centuries, it seems that the weather on Neptune is far more transient, with the largest events coming and going within the space of a few years. The intense weather systems that we witnessed on Neptune remain a tantalizing puzzle. The planet is on average 50% further from the Sun than Uranus, and receives just 40% of the sunlight that hits its sister world, and the surface temperatures of both planets are equally intensely cold. In fact, the temperature of Neptune's outer atmosphere is one of the coldest places in the solar system, with temperatures at its cloud tops measuring around minus 220 degrees Celsius. Orbiting this far out in the far frozen reaches of the solar system explains the blandness of Uranus's weather. But why would Neptune, even further from the Sun, be so active? The answer, we think, lies in a mysterious and powerful source of heat that we have detected coming from deep within the planet. All of the planets, including Uranus and Neptune, have some residual heat locked deep inside them, and much of this is the thermal energy that remains from the endless collisions of their creation, as well as the heat released by the radioactive decay of certain elements in the core. However, this far out, Uranus has rapidly lost this heat, and today radiates just 1.1 times the energy it receives from the Sun, so that the heat radiating from its core is too little to drive any kind of dynamic weather system through its atmosphere. Neptune, it seems, has a far warmer heart, and Voyager was able to reveal that the most distant planet radiates 2.61 times as much energy as it receives from the Sun. It's these unexpectedly high temperatures that help to explain the violent storms we see in its atmosphere. As the heat makes its way from the core of the planet and out into space, it churns up the entire atmosphere, creating winds of extreme ferocity, and once they start, there is little to stop them. Neptune, like Uranus, is an ice giant, a planet composed of a rocky core and a mantle made up of water, ammonia, and methane ices, surrounded by a cold gaseous atmosphere. With no solid surface on the planet, there are no mountains or continents to break up the flow of the atmospheric gases, so this means the winds can whip around the planet, picking up speed until they are quite literally supersonic. All of this helps to give us a reason for Neptune's extreme weather, but not an explanation. Voyager 2 was unable to reveal why Neptune and Uranus are so different, and we still don't know what it is about these planets' formation that left Neptune with far more residual heat, making it the far more active of the two. Neptune's active atmosphere was not the only surprise Voyager returned to us with the pictures from its two-camera system. In vibrant and vivid detail, the images also revealed the solar system to be home to not one, but 2 blue planets. Neptune is a bright blue world, but with no liquid water on its surface, we know that the origin of this color cannot be the same as here on Earth. This deep cobalt color must be produced by something else in Neptune's atmosphere, and Voyager provided the answer. Using its onboard spectrometer, Voyager was able to measure for the first time the composition of Neptune's atmosphere, and found it to be comprised of 80% hydrogen, 18.5% helium, and 1.5% methane. Methane was by far the smallest component, Yet this is the key to understanding Neptune's blue hue. The light of the sun contains all the colors of the rainbow, but as it hits the surface of a planet, it interacts in different ways depending on the molecules it encounters. In the case of the Earth, the water that covers our planet absorbs all of the red light in sunlight, so as the sun strikes the surface, only the blue is reflected back. It's the same with all the plants on our planet. The chlorophyll absorbs the blue and red light, so that only green is reflected back. On Neptune, there is no water to turn the planet blue. Instead, it's the methane that absorbs the red light of the dim and distant sun, reflecting the blue light back out into the darkness. But things aren't quite as simple as they first appear. Uranus is also a blue world, but just that bit paler and greener in shade compared with its more distant sibling. And yet Uranus also has methane in its atmosphere. In fact, it has slightly more. So Uranus, not Neptune, should be the darker shade of blue. Why is this? Well, quite wonderfully, we still don't know. Voyager looked for other constituents in Neptune's atmosphere that could account for the deeper blue, but it found nothing that could explain the discrepancy. So for now, the many differences between these two worlds remain a mystery. After over 12 years of travelling, Voyager 2 completed its grand tour of the solar system. A tiny explorer that had set out from Earth and travelled across 7 billion kilometres of space on a single extraordinary journey to explore all of the outer worlds of the solar system: Jupiter, Saturn, Uranus, and Neptune. But before it began its long, lonely journey into the darkness of interstellar space, there was one more brief rendezvous left on its itinerary. While in the Neptunian system, Voyager had made endless discoveries, including the detection of a faint ring system and the confirmation of 6 new moons in orbit. But in those final hours of close contact, as it flew across the north pole of the planet, the mission scientists back at JPL had instructed the craft to make one last intrepid maneuver, a close flyby of Neptune's giant moon, Triton. Just 5 hours after nearly touching the cloud tops of Neptune, Voyager travelled within 40,000 kilometres of the Neptunian moon and returned the first pictures of this strange and distant world. The British astronomer William Lassell first spotted Triton on the 10th of October 1846, just 17 days after the discovery of Neptune. As astronomers clamoured to observe the newly identified planet, it was Lassell with his homemade telescope who noticed the satellite first. Although not officially named until many years later, Triton would remain the only known satellite of Neptune for over 100 years, until the discovery of Nereid by Gerard Kuiper, more of him later, in 1949. As Voyager returned the first images of this distant moon, it immediately became apparent that, just like Neptune, Triton was far more active than we had ever imagined. Here in the furthest reaches of space, the 7th largest moon in the solar system was far from a frozen, inactive rock. It was a geologically active world, with features unlike anything we had imagined. Able to image just 40% of its surface due to the fact that most of the northern hemisphere was in darkness, Voyager revealed Triton to have a sparsely cratered exterior, with a strange network of ridges and valleys covering its entire surface, including in the western hemisphere, a region dubbed the Cantaloupe Terrain, because of its striking similarity to the skin of a melon. All of this evidence pointed to the fact that the surface of Triton was young, not battered and ancient like that of our moon, a surface that, even though it had been recorded by Voyager's instruments as one of the coldest places in the solar system at -235 degrees Celsius, seemed to be being resurfaced by active volcanism occurring across the planet. But this was not volcanism as we understand it here on Earth. There is no molten rock beneath the surface of Triton. This is an ice world, with a surface covered in a frozen mixture of nitrogen, water ice, and carbon dioxide. Any volcano that exists here would be a cryovolcano, erupting water, ammonia, and methane from below the surface. Cryomagma that would immediately solidify in the extreme low temperatures at the surface. And as Voyager peered closer at the surface of Triton, It captured a series of images of the southern polar region that appeared to provide evidence of such geological activity. Lurking amongst the flat volcanic plains and rift valleys was a set of distinct features that at once caught the eye. Scattered across the surface were what appeared to be at least 50 dark plumes. Voyager was travelling so fast and so far away from the Moon that it was unable to get close-ups of these intriguing plumes, but we are certain that they are the evidence of ice geysers, and that the dark streaks are dust deposits left on the surface by the eruption of these geysers. According to planetary scientist Noah Hammond, it was a big surprise to see active geysers going on Triton, shooting 8 kilometers into the air, and we think these geysers might be forming as a result of nitrogen ice which is being vaporized by the sun. Both of the geysers that Voyager 2 observed, which are currently blowing up, are concentrated on the warmest part of Triton, where the sunlight is striking the hardest. And as the sunlight pierces through the nitrogen ice, it starts to turn that nitrogen ice back into a gas again, and that gas builds up and builds up until it has enough energy to break through the ice and lift dust all the way up into the atmosphere. Further analysis of the images suggested that at least 4 of these geysers were active at the time of Voyager's flypast, belching clouds of ice and dust 8 kilometers up into the thin Neptunian atmosphere before falling back down to the surface over 100 kilometers downwind. Perhaps even more astonishingly, we have been able to actually formulate a hypothesis for the mechanism that lies beneath them. The key to understanding why this wondrous geological activity occurs in the most unlikely of places seems to involve their location on the surface of Triton. From the imaging data that Voyager 2 returned, it seems the geysers tend to erupt on the most sunlit part of Triton's surface. From a distance of 4.5 billion kilometers, the sun's rays are faint, and the amount of thermal energy landing on the surface is low. But combined with the specific chemistry on Triton's surface, the effect of the sun can still be dramatic. What seems to be happening is that sunlight falling on the thin layer of nitrogen ice that covers Triton is penetrating the surface and heating up a layer of darker methane particles, a meter below the surface. The methane acts as a subsurface greenhouse gas, trapping the heat below the surface and radiating that heat back up through the frozen nitrogen. Even though this mechanism creates a temperature difference of just 4 degrees Celsius between the ambient surface temperature and that of the warmer interior, this difference is enough to melt the frozen nitrogen and create pockets of gas. Sitting beneath the nitrogen ice, that gas is kept under pressure, building up until ultimately it punches through the nitrogen ice, creating the geysers of Triton and carrying the dark ice particles up to 8 kilometers into the sky. Although the faint light of the sun is just strong enough to power Triton's geysers, it's simply too weak to have driven the other geological processes that have created the network of valleys and crevasses we see all across the surface. It seems that something in Triton's past must have heated the Moon enough to drastically alter its terrain. And a potential clue to the source of that ancient heat can be found in the oddity of Triton's orbit. Unlike every other large moon in the solar system, Triton orbits in the opposite direction to the spin of the planet. Travelling around Neptune in its tidally locked orbit, with the same side facing inwards at all times, Triton orbits in a clockwise direction, while Neptune spins on its axis every 16.11 hours, anti-clockwise. Such dissonance between planet and satellite suggests that it is very unlikely that Triton and Neptune formed at the same time. A planet and moon system fashioned from an identical collapsing cloud of gas and dust at the same moment would tend to spin and orbit in the same direction as the spin of the initial dust cloud, just like the overwhelming majority of moons we see in the solar system today. So the most likely explanation is that Triton joined Neptune much later, a visitor to the Neptunian system that, unlike Voyager, never left. Like Uranus, we don't know for certain the deep history of Triton, but all the evidence from its orbit and surface features point to the possibility that long ago Triton was not a moon at all. To understand where it might have come from, we need to look beyond the Neptunian system and peer further out into the darkness. It was only relatively recently that we confirmed the existence of a region of the solar system now known as the Kuiper Belt, a disk of millions of objects that stretches out from the orbit of Neptune to at least 50 AU from the Sun. Similar to the asteroid belt in structure, but far larger in scale. We had long speculated that such a region might exist, but it wasn't until the discovery of an icy object known as 15760 Albion in 1992 that we were able to put together a body of proof. The discovery of this region was a turning point in our knowledge about our solar system. According to Alan Stern of the New Horizons mission, the Kuiper Belt was so revolutionary because, as it's so far from the Sun, the temperatures out there are almost absolute zeros, so everything is so well preserved. It's an archaeological dig, if you will, into the early history of our solar system. So it's a scientific wonderland, and you put all that together, redrawing the map and putting us in our place about who's the oddball now. It's not Pluto, it's the Earth or Jupiter that's the oddball. And then having this museum piece placed in the solar system where everything is so well preserved. I can't think of a bigger discovery that we've made that's reshaped our thinking so profoundly in all the decades of space exploration. Albion was the first trans-Neptunian object to be identified since the discovery of Pluto and its moon Charon. And this finding launched a flurry of further revelations that now put the number of identified objects in the Kuiper Belt region at around 2,400. We think there are at least 100,000 objects bigger than 100 kilometers wide in the Kuiper Belt. Just like the asteroid belt, this dispersed region of debris is composed from the remnants of our solar system's formation. But whereas the asteroid belt is a disk of rocky fragments, we think the Kuiper Belt is made up of icy objects, with methane, water, and ammonia the major ingredients. And it's that list of ingredients that leads us back to Triton and its strange history. We believe now that perhaps only Triton grew up out in the Kuiper Belt, amongst the millions of other frozen lumps of water, ammonia, and methane circling the Sun, before something such as a collision disturbed its orbit and flung it inwards. Plucked from the Kuiper Belt, Triton would be captured by the gravitational pull of Neptune and forever trapped in its strange orbit around the blue planet. Today, Triton orbits in a nice regular circle around Neptune, a bit like the way that our moon orbits around the Earth. But to begin with, this newly captured satellite would have almost certainly been in a chaotic orbit. Glancing past the planet, it would have started along a wide elliptical path around Neptune, bringing it from far out to close in on every revolution. This would have meant that as Triton orbited Neptune, the gravitational pull would be constantly changing, stretching and squashing the moon, just as Jupiter does to Io today, with the result that the friction of these tidal forces would have heated up the interior of Triton, creating far more activity than the erupting geysers we see today. Through this process of tidal heating, the ancient interior of ice would have become molten and volatile, exploding up through cracks and faults in the moon's crust, creating the ragged surface we see today. Over time, as the orbit adjusted into a more regular circular path, the friction reduced, the heating diminished, and so what we're left with is an icy, frozen moon circling the wrong way around its planet, the subtle scars of its early life written across its surface. All that remains today of that dramatic, violent past are the geysers, powered by the faint light of the sun, painting dark streaks across the now quiescent surface. As Voyager 2 sped away from Triton and Neptune at over 60,000 kilometers per hour, the planetary exploration phase of this extraordinary mission finally came to an end. Its exploration would continue beyond even the furthest reaches of our solar system, and would extend into the unknown depths of interstellar space. But its time as a planetary explorer was over. A tiny spacecraft, built with 1,000 human hands, had shone a light into the darkness, revealing the secrets of worlds that had been hidden in the night for over 4 billion years. As yet, we have not returned. But while Neptune and Uranus have fallen back into the distance, viewed only through the lenses of our most powerful telescopes, another, even more distant world was out there waiting for our first arrival. On the night of the 23rd of January 1930, a 23-year-old junior researcher at the Lowell Observatory in Flagstaff, Arizona, took an image of the night sky using a 13-inch astrograph, a telescope designed for the sole purpose of astrophotography. Clyde Tombaugh had been at the observatory for just over a year when he took the image, one of hundreds he had captured over previous months. A keen amateur astronomer, he had landed this first job after sending in a series of drawings he had made of Jupiter and Mars using telescopes he had built at his home. Every night at the Lowell, Tombaugh performed the same task, using the astrograph to photograph a precise section of sky that he would then image again a few nights later. The task was a little laborious, but its purpose was profound, because hiding within the near-identical images, Tombaugh was on the hunt for a new world, the enigmatic Planet X. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets and taken our first steps into the outer reaches of the solar system beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound, and the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the Moon bears testament to a record of violence and destruction from the skies that the Earth has also endured, but the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited Sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system, has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, but we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, an active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the 3 large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All 3 worlds may once have been habitable, and all 3 worlds may once have harbored life, but now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the ways by which we could destroy our civilization, because it shows us what greenhouse gases can do to a world. I think one of the reasons why anthropogenic climate change is so difficult for a certain type of person to accept is that atmospheres seem ethereal and tenuous. and incapable of trapping enough heat to modify the temperatures on a planet significantly. For such people, I suggest a trip to Venus, where they will be squashed and boiled and dissolved on the surface of Earth's twin. The exploration of the planets, then, is not an indulgence. If we want to know how we came to be here, we need to understand the histories of the planet that gave birth to us, and the system that gave birth to it. We are children of Earth, and also children of the solar system. Understanding our history is important because it places our existence in context. The more we learn about the events that led to the emergence of humans on this planet only a few 100,000 years ago, the more we are forced to marvel at the sheer unlikeliness of it all. We needed Jupiter and the comets and asteroids and countless collisions and mergers and near catastrophes stretching back 4.6 billion years. There are valid objections to this way of thinking. It is an objective fact that we are here, and our future should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the Earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future. Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold, with surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but a billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the timescale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core, our planet and the civilizations it once harbored will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation. This swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car. and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over a kilometer in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings two or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different, and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other, and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology. which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets, but it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the Sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the Sun twice to have one complete solar day on the planet, where the Sun goes from directly overhead to directly overhead, and this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky Sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun, except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are 2 major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen-Wan Yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometer trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist maneuvers around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years. Too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain, Mercury's ancient surface is the most cratered place in the solar system. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Caloris Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Caloris to be bigger than had been previously estimated, encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Caloris hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the weird terrain, a region at the planet's diametrically opposite point, the antipode to Caloris. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Caloris impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, these regions are forever exposed to the freezing temperatures of space. And it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur at much higher levels than they were expecting. Up to this point, the working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the Messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the Messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the Messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. Mercury, like all 4 of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the Sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun. But these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future, or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, And that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of Messenger did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But Messenger's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, Messenger found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer, possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, Messenger finally ran out of fuel on the 30th of April 2015 and added yet another crater to this tortured world that once held such promise. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, this is a planet that holds its secrets close. For centuries, it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century, we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, he suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect. An effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Arrhenius had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970 and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet. 4 billion years ago, Venus was a familiar world, a world created from the same dust as the Earth, born just about the same size, and settled into an orbit that seemed just far enough away from the glare of the sun to allow a precious process to begin to take hold. In almost every conceivable way, Venus's early life mirrored that of our own world. As its newly formed crust settled and cooled from the violent heat of its birth, an atmosphere began to grow around the young planet, fed by gases bubbling up from the molten rock below its surface, as well as captured from the clouds of gas and dust it swept through on its orbit around the Sun. Clinging to the young Venus, this thin layer of gas would have certainly contained nitrogen, oxygen, and carbon dioxide. But most intriguing of all, we are certain it would have also contained large amounts of water vapor. High in the Venusian atmosphere, this water vapor eventually cooled enough to change state from vapor to liquid. And with that transformation, a process began that perhaps for the first time on any of the planets would have seen the conditions become just right for droplets of liquid water to take shape and begin falling from the Venusian sky. These were the first rains of the solar system, showering down onto the dry plains of Venus. Gradually these rains would have not just fallen but flooded the surface. Rivers would have flowed, and shallow oceans taken hold of large swathes of the planet's surface. Venus, perhaps before even the Earth, became a water world, a planet with skies full of clouds and a surface full of oceans, feeding the cycle of water around this young planet. How can we be certain this blue version of Venus existed? Unlike Mars, where we can see the evidence of its watery past etched onto its surface, we have no such direct evidence of the presence of liquid water on the surface of Venus. The only physical evidence we have that suggests the planet's watery past comes from measurements taken by NASA's Pioneer Venus spacecraft back in 1978. One of its most surprising discoveries revealed an unexpected amount of deuterium, heavy water, in the atmosphere compared with hydrogen. This DH ratio is far smaller on Venus than it is on Earth, and that's interesting because when the two planets formed, the ratio would have almost certainly been the same. Because hydrogen is far more easily lost from an atmosphere than deuterium, this smaller ratio suggests that Venus has lost a lot more water than the Earth over its lifetime, the signature of a long-lost primordial ocean, as cosmochemist Larry Nittler explains. Scientists believe that Venus once had a lot of water in its oceans, but lost it over time, and perhaps in oceans as recently as 1 billion years ago. The reason we can tell this is from the isotopic composition of hydrogen measured in its atmosphere by spacecraft. Now, hydrogen has 2 flavors of isotopes. Whereas most hydrogen atoms are just a single proton in the nucleus, some, a small fraction, are what we call deuterium, that have a proton and a neutron, so they weigh twice as much as the regular hydrogen. What happens when you have evaporation of water from a planet, or the atmosphere, is that the water molecules that contain hydrogen are much lighter than the water molecules that contain deuterium, so they evaporate more easily and can be lost more easily. So over time, as you evaporate water, deuterium-bearing molecules stay behind relatively to the regular ones, and you build up a deuterium to hydrogen ratio. And by back-calculating from the measured ratio today, we can figure out how much water has been lost over the billions of years of evolution, and on Venus, it's quite a lot. None of this is solid proof, but it does begin to point us in one direction, and with no further exploration of the surface, we've had to rely on an accumulation of indirect evidence to begin to paint a more detailed picture of Venus's watery past. As with almost all of our understanding of the planets, the evidence that built this picture has been accumulated through decades of exploration. Starting with the Venera mission's first touchdown on the planet, to the Pioneer Venus orbiter, and to the more recent Magellan mission, which not only relayed extraordinary radar soundings of the surface of Venus, but provided the first full topographical map of the planet collated over a period of 4 years in orbit. Combining all of the data that has been accumulated over decades of exploration has allowed us to peer deep into the planet's past, using the same tools that enable us to model the future of climate change here on Earth, to create climate models of Venus in the past, present, and future. The results of this analysis, conducted most recently by a team from NASA's Goddard Institute for Space Studies, GISS, all point to the same conclusion. In the distant past, Venus was a planet covered in shallow, primordial oceans. Some estimates suggest that this water world was far from fleeting, a blue planet just like our own that could have been sustained for around 2 billion years, and perhaps only disappeared some 700 million years ago. It's a tantalizing thought that such a similar world to our own existed for so long with liquid water on its surface. We know life took hold quickly on our own blue planet, within 500 million years of the Earth being formed. So there seems good reason to suspect that if Venus really was as wet as the models predict, it too could have sprung into life. Exactly what went on in the long-lost rivers and oceans of Venus is yet to be discovered. Hidden behind the clouds, we have not yet been back to search for any signs that life ever took hold here. Our exploratory attentions have turned to Mars as a planet that not only has a fertile past, but is also a possible target for human colonization in the future. We know for certain that no life, at least no life we understand, could exist on Venus today, and perhaps even the evidence of any biology on that long-lost water world has long ago vanished under the oppressive heat, rampant volcanism, and extreme pressures of the planet today. Today, Venus has the slowest rotation of any planet in the solar system, taking 243 Earth days to complete one rotation on its axis. This period is known as the sidereal day, which is different to a solar day, the time it takes for the Sun to return to the same point in the sky. On Earth, the sidereal day at 23 hours 56 minutes and 4.1 seconds is very close to the solar day, which lasts pretty much exactly 24 hours. But on Venus, the difference between these two periods is much greater. Even though the planet takes 243 days to rotate on its axis when combined with its orbit, a solar day on Venus lasts for 116.75 Earth days. It means every day on Venus lasts almost 4 months on Earth. And not only that, but Venus also rotates from east to west, one of only 2 planets to do so, along with Uranus. So across this toxic world, a sunrise would last literally for days as it inches across the sky. This slow progression of the Sun in the Venusian sky, due to the planet's creeping rotation, has raised many questions about how in the past the planet would have been heated, and how the climate would have been affected by such a different rotation compared with the Earth's. Today, the climate of Venus is what is known as isothermal. There is a constant temperature between the day and night sides, and between the equator and the poles. This is because the thick atmosphere literally acts like a blanket, dissipating the heat of the Sun so that the only real variation in temperature on the Venusian surface occurs due to differences in altitude. In its past, however, this may have been very different. With a more Earth-like atmosphere, so the Sun would have been beating down on the planet's surface for days on end. To make things even more complex, we know the spin of a planet is intimately linked to its climate, and we've got strong evidence to suggest that how fast a planet spins is directly related to its chance of habitability. Until very recently, it was assumed that the slow rotation of Venus must have been caused by the presence of a thick atmosphere early on in its history that in effect acted as a brake on the planet's spin. However, recent studies now suggest that the planet could have had a thin atmosphere like that of modern Earth, and still have ended up with its slow rotation. Gradually, as we start to build a picture of ancient Venus, we begin to see beyond the cloud cover of today, through to an ancient planet with an Earth-like atmosphere, and a day lasting over 200 Earth days as the Sun beat down on the ocean-covered surface. To make sense of the climate of this Earth-like Venus, the team at the Goddard Institute needed to make another tweak, or postulation to be more precise, to the model. With the Sun hitting the one side of the surface for so much longer than on the Earth, the evaporation rate of the oceans would be far greater and potentially incompatible with the water world we suspect existed. But by simply adjusting the amount of dry land on the surface of Venus, especially in the tropics, the effect is dramatic. With a higher percentage of land, the models suggest that even the slow rotation would not dry out the planet, and it could have held on to enough water to be ripe for supporting the emergence of life. By combining all of this data, the GIST team have painted our most up-to-date picture of early Venus. And it's a beguiling image. Within the infant solar system, it is a planet the size of Earth with similar atmosphere to the one we see today. On Venus, days lasted for months as the sun arced slowly across the sky from west to east, rising and setting over a vast, shallow ocean. Finally, the data from radar measurements taken by NASA's Magellan mission in the 1990s was used to paint the last brushstrokes of this long-lost world. Filling in the lowlands with water, the topography of this ancient world emerges, with the highlands exposed as the Venusian continents. It all points to the possibility that Venus could have been the first habitable world in our solar system. So what changed? To find out, we need to look not just at the planet in isolation, but also at the star around which it orbits. No planet lives out its life in isolation. Venus, like all the planets, is not just part of a configuration of planets and moons, asteroids and comets, but is also part of a solar system, a system that is driven more than anything else by the star at its center. Today, the sun burns bright in our skies, bathing our planet in just enough starlight to keep the oceans from freezing, but not too much to boil them away. Earth lies in the sweet spot we call the Goldilocks zone, but as we have already seen in this chapter, nothing in the solar system is forever, and what we see today is not what we will see tomorrow, nor what we would have seen yesterday. As our sun gets older, it's gradually burning hotter and hotter. This is because as it ages, the process of nuclear fusion, the fusion of hydrogen into mainly helium, gradually leads to an increase in the amount of helium in its core. This rise in helium causes the sun's core to contract, which in turn allows the whole star to shrink in on itself, creating an increased pressure that results in a rise in the rate of fusion, and so the energy output of the sun goes up. If tomorrow the sun is burning hotter than today, it of course makes sense that in the early days of the solar system, our sun burned far less brightly. It's a life cycle that is common to all main sequence stars, the category of star that includes our sun. And as the most common type of star in the universe, we've been able to study this life cycle in intimate detail, allowing us to make immensely detailed predictions about the characteristics of our sun in the past and in the future. Winding back the clock, the current consensus among astronomers is that 4 billion years ago, the faint young sun was at least 30% dimmer than it is today. This cooler sun would have undoubtedly had a big impact on all of the terrestrial planets. Earth would have been much colder, and as it was receiving far less solar energy, it remains something of a mystery as to why our planet wasn't frozen solid. Instead, at this time on Earth, first life was just beginning, in the liquid water that we are pretty certain covered its surface. At the same time, 3.5 to 4 billion years ago, the young sun would have bathed Venus in a warmer glow. This ocean world found itself in its very own sweet spot, a world held in a delicate balance. With the sun weakened and restrained, the Earth-like atmosphere of Venus could act as a gentle blanket, keeping the surface temperate and covered in an abundance of liquid water. But even with this additional solar energy, we think Venus would still have been much cooler than the Earth is today. In fact, we believe temperatures at that time would have been like a pleasant spring day here on Earth. It wasn't to last. Slowly the young sun grew brighter, its increased energy output causing temperatures to gradually rise, which in turn began to lift more and more water vapor into the air, thickening the atmosphere and sealing the planet's fate. Although the oceans of Venus may have persisted for billions of years, as the surface warmed and the atmosphere thickened, the destiny of this planet was already set. driven by an unstoppable process we have recently become very familiar with here on Earth. The greenhouse effect is a process that has the power both to protect and to destroy a planet. But despite this power, it actually boils down to some pretty simple physics. It's all about how sunlight, solar radiation, interacts with the constituent parts of an atmosphere. In the case of the Earth, as solar radiation hits our atmosphere, some of it is reflected straight back out into space, some is absorbed by the atmosphere and clouds, but most of the sunlight, about 48%, passes straight through the atmosphere and is absorbed by the Earth's surface, where it is heated up. The reason so much solar radiation makes it to the surface is because the gases in our atmosphere, like water vapor and carbon dioxide, are transparent to light in the visible spectrum. When you think about it, that's pretty obvious because there's a source of visible light in the sky, the sun, and we can all see it. But it's a different story when that sunlight heats the surface of the Earth and re-radiates back out, not as visible light, but as the longer wave infrared light, thermal radiation. We can't see this light, but as it radiates back out from the Earth's surface, carbon dioxide and water vapor absorb the infrared, trapping that energy, and so the planet maintains a higher temperature that is intimately linked to the constituent parts of the atmosphere. The higher its level of gases like water vapor, carbon dioxide, methane, and ozone, the greater the greenhouse effect and the bigger the uplift in temperature. Despite the very real threat that this now poses to the future of our planet, the greenhouse effect on its own is not necessarily a bad thing. The Earth would be at an average temperature of around -18 degrees Celsius without it. But as we are currently witnessing here on Earth, shift the balance of those gases, and things can change very quickly. At some point in Venus's past, the levels of water vapor lifted into the atmosphere by the warming sun pushed the greenhouse effect to become precariously more intense. With less and less of the sun's energy escaping, the ambient temperatures began to rise exponentially, until the day came when the last raindrops fell onto the surface of the planet, the heat evaporating the rains long before they could reach the ground. Venus had reached a tipping point. With the increasing temperatures feeding more and more water vapor into the atmosphere, a runaway greenhouse effect took hold, driving away the oceans. This led to the surface of the planet getting so hot that carbon trapped in rocks was released into the atmosphere, mixing with oxygen to form increasing amounts of another greenhouse gas, carbon dioxide. With no water left on the surface and no other means to remove it, carbon dioxide built up in the atmosphere, setting the planet on a course that would result in the scorched body that we see today. And so Venus's moment in the sun came to an end. Earthlings, take note. When it comes to the greenhouse effect, there is a precariously thin line between keeping a planet warm and frying it. Of the 4 rocky worlds, only one has managed to navigate through the instability and constant change of our solar system over the last 4 billion years and maintain the characteristics needed to support life. Mercury lost its fight early as it was flung inwards towards the sun. Venus flourished at first before slowly coming to the boil, and Mars, the runt of the litter, became a frozen wasteland long ago. Only Earth, uniquely among the planets, has persisted with an adequate stability over the last 4 billion years to allow liquid water to remain on its surface and an atmosphere just thick enough to keep its climate calm, not too hot and not too cold. Events have rocked us, and extremes of temperature have waxed and waned, but never outside of the parameters needed to harbour life. In a chaotic solar system filled with planetary might-have-beens, Earth is a shining example of stability, and the evidence for this is to be found in every nook and cranny of the planet. Today, Earth is dominated by life. The land and seas are teeming with millions upon millions of species, with thousands of new life forms discovered each year, Somehow, even when disaster threatened, the Earth has remained a living world. While endless species have come and gone, life has always persisted. It's woven into the fabric of the planet, an integral part of every continent and every ocean. Life plays a crucial role in maintaining the balance of the atmosphere that keeps our planet temperate. But we know for certain it cannot last. The Kamchatka Peninsula in eastern Siberia is one of the most inhospitable places on Earth. A volcanic wasteland, peppered with thousands of hot springs, it's here that we find some of the toughest living things. Extremophiles survive here that are able to withstand temperatures and pH levels higher than any other land-based life forms we have ever discovered. Kamchatka is part of the Pacific Ring of Fire, and despite its remoteness, biologists have long been enticed here to explore its toxic, bubbling cauldrons for signs of life. Complex life, animals and plants, struggle to survive in temperatures above 50 degrees Celsius. So searching for life here is all about searching for single-celled life forms, bacteria and archaea, ancient microorganisms, that are somehow able to endure in this hostile environment. Life forms like Acidilobus aceticus, an archaea that can be found in a hot spring where the water is so acidic it reaches a pH of 2, and where temperatures rise to 92 degrees Celsius. In other parts of the hydrothermal field, bacteria like Desulforella acetivorans have been discovered, which happily live in pools that are touching 60 degrees Celsius, but it's these that are the real hotheads. In one of the biggest and hottest pools investigated by scientists, a large number of microbes have been found living in temperatures approaching 97 degrees, making it one of, if not the, hottest environment ever studied for signs of life on land. But to find the greatest hotheads on planet Earth, you need to look not on land, but deep beneath the sea. In the furthest depths of the Atlantic, around the black smoker hydrothermal vents blurting out of the ocean floor, we found strains of archaea that can survive temperatures of 122 degrees Celsius, and perhaps even higher. These rare life forms live at the very edges of biology. Unique adaptations to their cellular chemistry enable the proteins and nucleic acids that create the structure of the microorganism to function, while the membranes that are protecting the cells utilize different fatty acids and lipids to keep the cells stable at the higher temperatures. Perhaps there are even tougher life forms that we are yet to discover, but the thermophilic microorganisms that we have so far identified and investigated in places like Kamchatka all point to the fact that life has its limits. Evolution by natural selection can only adapt so much, and even though it's impossible to imagine what life on Earth will look like in a few 100 million or even a few billion years' time, we know that biology is constrained by thermodynamics. And so we can say with some certainty that there will come a time when the Earth is too hot for any living things to exist. Natural selection will eventually run out of options as the laws of physics outplay it, and all life will come to an end. When this will happen, no one can be certain. But as the sun ages and grows hotter, temperatures on Earth will rapidly rise. Today, the average surface temperature on the planet is 14.9 degrees Celsius. But with just a 10% rise in the sun's luminosity, the average temperature will rise to 47 degrees Celsius and climbing. The increased temperatures will raise great storms across the planet. The rains will remove carbon dioxide from the atmosphere, and it will be locked away as newly formed sedimentary rock. Trees and plants will struggle as they are robbed of the gas that sustains them, until eventually photosynthesis will cease. The lungs of our planet will fail, and the precious oxygen that green plants and algae produce will dwindle. With the primary food source gone, the food chain will collapse and the age of complex life on Earth will draw to a close. Heat-loving extremophiles may flourish for millions of years more, but eventually nuclear physics will have its way, and as average temperatures race above 100 degrees Celsius, the last pockets of life will be extinguished from the Earth. We can say with confidence this is going to happen because we can plot the future of our Sun far more precisely than the future of the Earth. Our understanding of nuclear physics allows us to predict what happens inside the cores of stars, and thus we can see the past, present, and future of stars like ours written across the night sky. The heavens are filled with shining examples of stars that give us a glimpse into the future of our Sun. Arcturus, for example, in the constellation Boötes, is one of the brightest stars in the northern hemisphere. It's around the mass of the Sun, perhaps a little bit heavier, and so in the distant past would have had remarkably similar characteristics to our own star. Today, though, Arcturus is 6 to 8 billion years old, potentially 3 billion years older than the Sun, and as it is no longer a main sequence star, it is now in the red giant phase. Its fuel exhausted, it has swollen up to 25 times its original diameter, and is around 170 times as luminous, despite the fact that as its core slowly burns out, it is cooling. To see even further into the future, we need to look towards the brightest star in the northern sky, Sirius. The dog star, as it's commonly known, is twice the mass of the Sun and still fully in the main sequence. But obscured by the glare of Sirius A is a faint companion, Sirius B. This is a star that has already burnt through its fuel, swollen into a red giant, and the outer layers have drifted off into space, leaving the fading core of the star about the size of the Earth, known as a white dwarf. These stars are just two examples amongst many that point us towards the ultimate fate of our Sun, a fate that we believe will play out over the next 5 billion years or so. Just like Arcturus, as the Sun exhausts its hydrogen fuel, its outer edge will inflate and it will enter a red giant phase. Expanding millions of kilometers out into space, it will engulf Mercury first. Venus's fate will be sealed next as the Sun expands further. Some models predict that Earth may just escape the fiery end of its neighbors, heated to 1,000 degrees Celsius, but hanging on beyond the edge of the dying star as its orbit extends out due to the lessening mass of the Sun. Dead but not destroyed, Earth and Mars will orbit as burned-out relics of their former selves. The era of the 4 rocky inner planets will be over, the billions of lives lived on the surface of one of them nothing but a distant memory. But within our solar system lies another family of rocky worlds, whose moment in the Sun may be to come. Far beyond the asteroid belt, millions of miles away from the sun-drenched planets of the inner solar system, the gas giants of Jupiter and Saturn are home to another family of rocky worlds. Jupiter alone has 79 known moons orbiting it, a menagerie of satellites of multiple shapes and sizes. We've been peering at these moons since Galileo Galilei spotted 4 of them, Io, Europa, Ganymede and Callisto, known as the Galilean moons, over 400 years ago, with his telescope transforming our understanding of our place in the solar system. Today we have explored the Galilean moons not just from afar, but close up, and found them to be dynamic worlds. Io is fiercely volcanic, and Europa, the ice moon, shows tantalizing evidence on its surface pointing to a subsurface ocean sitting below its icy crust. Ganymede and Callisto make up the final 2 Galilean moons, and just like Europa, they are rocky worlds with an abundance of water ice on their surfaces, and perhaps their own oceans lurking beneath. These 3 rocky, frozen worlds are all sitting in the cold outreaches of our solar system, touched by the distant Sun but barely warmed, lying dormant until perhaps one day the aging Sun will reach out and turn these bodies into ocean worlds for the very first time. The next planet out, Saturn, also has its ever-growing family of moons. Amongst its collection of over 60 confirmed satellites are Titan, the only known moon with a dense atmosphere and liquid lakes on its surface, though they are primarily methane, not water, and Enceladus, a frozen ice moon just like Europa with a liquid ocean deep beneath its ice. Until we go back and explore further, we can't be certain what lies below its surface. But the possibilities that the Cassini probe has so tantalizingly hinted at make it one of the most exciting places for us to visit within the next generation of interplanetary expeditions. All these ice worlds, sitting dormant in the frozen reaches of the solar system, offer the promise of a very different future, one in which the rocky worlds of the inner solar system have been reduced to cinders, and a new generation of worlds waits to awaken. Ice worlds will become water worlds, warmed by the expanding sun, until our dying star ultimately collapses into a white dwarf. Mars is a mirror for our dreams and nightmares. To the naked eye, the planet exhibits a reddish hue, blood red in the imagination, god of war, star of judgment. Through a small telescope, it is the most Earth-like of planets, with cinnabar deserts and white polar ice caps. A world we could imagine visiting, perhaps even settling in. 19th century astronomers convinced themselves they saw plains and mountain ranges, and canals delivering meltwater from high latitudes to arid equatorial cities. Some thought the Martians a peaceful civilization, far in advance of our own. Others saw threat. Across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes, wrote H.G. Wells in his classic science fiction novel The War of the Worlds in 1897. The nature of Mars remained a mystery until well into the 20th century, because the planet is small and far away, and therefore difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images which would not at first sight have prevented Wells from publishing. With a little imagination, the ice caps, high clouds, and dark regions circling the deserts could be mistaken for evidence of a water cycle feeding the seasonal advance and retreat of vegetation. Photographs from the first flyby of Mars by NASA's Mariner 4 spacecraft on the 15th of July 1965 abruptly laid to rest the romantic notion of Mars as Earth's habitable twin or potential foe. These images revealed an arid surface reminiscent not of our blue planet, but of our desiccated moon. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. And contemporary accounts of the impact of the Mariner 4 flyby suggest that this was a powerful realization. In November 1965, the Bulletin of the Atomic Scientists carried an article entitled "The Message from Mariner 4," and the message was bleak. The shock of Mariner's photographic and radiometric reports is caused not only by their denial of the terrestrial image of Mars, but by the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson was reported as commenting, it may just be that life as we know it, with its humanity, is more unique than many have thought." The hesitation in the first few words is revealing. Here is Mars as a symbol of our cosmic isolation. It is as though deep, or perhaps not so deep, in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that the Earth is far more fragile and precious than a dispassionate analysis of their Cold War brinkmanship might suggest. Or perhaps the perspective delivered by exploration is always shocking. Apollo 8's Earthrise, the photograph that delivered such a positive end to a troubled 1968 by setting the blue Earth against the grey moon, was 3 years away. But Red Mars provided a foretaste. In response, Carl Sagan co-authored a paper suggesting, somewhat playfully, that all was not lost. Mariner 4 took only 22 photographs with a resolution of over a kilometre, in a strip crossing the region in which the astronomer Percival Lowell had sketched canals from his observatory in Flagstaff, Arizona at the turn of the 20th century. From the warmth of the Arizona desert, Lowell wrote that Mars was chilly, but no more so than the south of England, which certainly supported a civilization of sorts. Using several thousand photographs of a similar resolution taken by meteorological satellites in Earth's orbit, Sagan and his co-authors found only a single feature that unambiguously indicated the presence of a civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization had it flown by Earth. We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it. The non-existence of an extant Martian civilization was confirmed by the Mariner 9 mission in November 1971, the first spacecraft to orbit another planet. Mariner 9 achieved a photographic resolution of 100 meters per pixel, and no sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the combined results of the suite of microbiology experiments carried by the spacecraft are not considered to be unequivocal, because Martian soil chemistry is, to coin a phrase from the official NASA report, enigmatic and could conceivably have masked any biological activity. In hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles further from the Sun than Earth and receives less than half the solar energy. It is a small world with a tenuous atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in the Gale crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning it has experienced minus 120. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than of intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides, and rivers wound their way through valleys, carved by a water cycle from land to sky and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock because it is a small planet far from its star. But the geological evidence is unequivocal. The surface tells a different story. Mars, then, remains an enigma. As a wandering red star, it stirred the imagination of the ancients. As a telescopic image, too small and shifting for visual or intellectual clarity, it became our twin. When spacecraft flew by, it shocked us into considering our cosmic isolation. The red planet was relegated in our collective consciousness to the status of just one more rock, glistening in the night. Then we landed, and discovered a world that was once habitable, and could be again. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity and volcanism have erased the deep geological past, Mars has been relatively quiescent for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient cataclysms documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s and provided detailed maps with colors corresponding to differences in altitude. Just as on Earth, there is significant variation, but the geological features on our smaller sister world are much bigger and bolder. The highest elevations on Mars are found on the Tharsis Rise, a great volcanic plateau and home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Everest, Olympus Mons towers 25 kilometers above the lowlands of Amazonis Planitia to the west, and its base would fit inside France just about. Cutting a deep scar across Tharsis to the southeast of Olympus Mons is Valles Marineris, named after the Mariner 9 spacecraft that discovered it, a canyon that dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. The atmospheric pressure at the floor is twice that at the rim, high enough for liquid water to exist on the surface in a narrow range of temperatures. These are extreme altitude differences for a small world. Over 30 kilometers from the summit of Olympus Mons to the floor of Hellas. On much larger Earth, for comparison, there is only 20 kilometers difference between the summit of Everest and the Challenger Deep in the depths of the Mariana Trench. The most striking and ancient elevation difference on Mars is that between the northern and southern hemispheres of the planet, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometers lower in altitude than the southern. There is no consensus as to how the dichotomy formed, other than that it was early in the planet's history, and before the large impacts which created the Utopia and Chryse basins around 4 billion years ago. At some later time, the northern lowlands were resurfaced by volcanic activity in a similar fashion to the smooth lunar seas, which accounts for their lack of cratering relative to the much more ancient terrain to the south. The oldest terrain on Mars is found in the Noakis Terra region of the southern highlands. It is characterized by heavy cratering reminiscent of the far side of the Moon. Even small craters in the Noakian highlands are heavily eroded, which suggests the regular, if not persistent, presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls, forming interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world, at least occasionally. The evidence is written across the land of Noah. In contrast, the younger terrain of Hesperia Planum displays much less evidence of regular erosion by water, but bears the scars of occasional catastrophic floods that cut deep valleys over very short periods of time, and may have formed temporary large lakes or seas. The Amazonis Planitia region shows little sign of flowing water, fewer impact craters, and less evidence of active volcanism, suggesting it was formed more recently, when Mars was significantly less geologically active. The persistence of surface features over many billions of years in the Noakian, Hesperian, and Amazonian regions has led to the historical epochs of Mars being named after the distinctive terrains that still bear the characteristic marks of the climate and geological activity that formed and sculpted them. The Noakian period was the earliest and wettest, and coincided with the origin of life on Earth around 4 billion years ago, when conditions on both worlds appear to have been very similar. The Martian atmosphere may have been denser than Earth's and dominated by carbon dioxide, but significant questions remain about how such an atmosphere could have warmed Mars sufficiently to deliver the warm, wet climate, and how that atmosphere was lost. The MAVEN spacecraft, currently in orbit around Mars, aims to answer this question. The Noakian period ended as Mars became increasingly cold and arid around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period, the time of catastrophic floods, ran from the end of the Noakian to around 3 billion years ago, when Mars entered its current frozen, arid phase, punctuated by occasional volcanic activity and the large-scale movement of ice, but with very little evidence of flowing water. The long 3 billion-year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The whys pose a significant challenge to planetary scientists. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day aridity? What happened to the water on Mars? Was it lost to space, or does it persist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still accessible? Could we exploit the ancient reservoirs of Mars to support a human colony? And perhaps most significantly of all, did life arise on the planet during the Noachian period, coincident with the origin of life on Earth? And could that life still be present on Mars today? The current fleet of spacecraft in orbit around Mars and roving across its surface has been designed to answer these questions. Mars today is a planet buzzing with activity. Communications to Earth and the Martian Internet are managed by the Mars Reconnaissance Orbiter, MRO, an orbiting bridge between worlds. MRO carries the HiRISE instrument, a camera with resolution high enough to see basketball-sized features on the Martian surface. The Mars Color Imager Marquee camera monitors Martian weather, and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, identifies mineral deposits, particularly those formed in the presence of surface water. Orbiting with the MRO is the Mars Atmosphere and Volatile Evolution Mission, MAVEN. This cameraless spacecraft operates between 150 kilometers and 6,000 kilometers above the Martian surface, measuring the composition of the atmosphere at different altitudes and observing how the tenuous gases are stripped from the planet by the solar wind. Mars Odyssey is the veteran of the orbiting fleet, having arrived in 2001 and still being operational in a polar orbit, searching primarily for water ice on the surface. Mars Express is a European Space Agency mission that is delivering high-resolution photographs, mineralogy data, radar investigation of the near subsurface, and atmospheric measurements, including the search for methane, a gas that on Earth is associated with biological activity. India's Mangalyaan space probe is primarily a technology demonstrator, but it carries a secondary scientific package capable of investigating atmospheric composition. The newest arrival at Mars is the joint European Space Agency Russian ExoMars Trace Gas Orbiter, which will observe seasonal changes in the Martian atmosphere and search for subsurface water deposits. The spacecraft will form the communications bridge for ESA's ExoMars rover, due to land in 2021. The two most recent explorers of Mars are the Opportunity and Curiosity rovers. The Opportunity rover landed on the Meridiani planum close to the Martian equator on the 25th of January 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to the Jet Propulsion Laboratory's engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018, after over 14 years and a journey of 45 kilometers on the surface of Mars, exploring the Endurance, Victoria, and Endeavour craters. On the 13th of February 2019, Opportunity was finally declared dead. Opportunity's younger and far larger companion on Mars is Curiosity, the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. The enormity of the mission is best described through the words of Alan Chen, operations lead at NASA for the Curiosity mission, at 10:31 PDT on the 5th of August 2012, watching the landing at the Jet Propulsion Laboratory alongside the team. The engineers described it as 7 minutes of terror. 7 minutes to maneuver a spacecraft that had taken 8 years to design and build, with a program cost of more than $2.5 billion, from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface of the planet. The tension reflected the high stakes. The Mars Science Laboratory mission, to give the lander and orbiter their full title, was a high-risk flagship science mission in the same category as Voyager, the Hubble Space Telescope, Viking and Cassini, and was beset by cost and schedule overruns and controversy. This is in many ways unsurprising. New technologies and ambitious scientific objectives are difficult to implement and achieve, and in part because of this deliver great rewards. In hindsight, nobody would question the value of any of these missions, which have delivered some of the greatest insights and most inspiring images in the history of exploration. Yet this never prevents bean counters and rival scientists with agendas, and more charitably, budgetary challenges of their own, whinging and even considering cancellation. This is naive. Funding for science is almost always grudging from a political class whose view of the acquisition of knowledge is utilitarian. The far deeper value of exploration as a critical part of the internal voyage of our species, bringing us into direct confrontation with the mystery of our existence, is lost on them, at least until occasional Johnsonian, President, not Alexander Boris de Pfeffel, moments. It may just be that life as we know it with its humanity is more unique than many have thought, and we must remember this. Which means that a cancellation of one project does not mean an uplift in funds for another. More likely the budget will be lost to science. At the time of writing, the same issues plague another NASA flagship mission, the James Webb Space Telescope. As Robert D. Baum wrote in an op-ed article for Space News in December 2008, at the height of the Mars Science Laboratory controversy, when implementing flagship missions, cost and schedule overruns are not uncommon. But history shows that the mission return often eclipses the expenditure. The Hubble Space Telescope experienced a development cost overrun several times its approved project budget, and was launched much later than originally planned. In hindsight, would any rational space scientist not concede that the return from Hubble was worth the investment? Given the febrile atmosphere, however, no amount of philosophy or reason would mitigate the costs of failure of the Mars Science Laboratory mission. A landing accident was both possible and unthinkable. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not trivial, which is perhaps why the chosen engineering solution seemed, not to put too fine a point on it, daring. Mars has a thin atmosphere, so slowing down a spacecraft when it's traveling around 10 times faster than a bullet is hard. And yet the atmosphere is thick enough to apply sufficient frictional heating to destroy a spacecraft without adequate protection, and turbulent enough to cause significant uncertainty in the landing site of an unsteered vehicle. This renders the more obvious engineering solutions redundant. You can't simply deploy a parachute and float to the surface. The 1970s Viking landers used a combination of heat shields during aerobraking, parachutes, and retro-rockets with success. But the Curiosity engineering team dismissed this tried-and-tested solution. It did not allow for high enough precision, or for the gentle landing required for the pinpoint delivery of a large rover with delicate wheels. The Viking landers had legs built like tanks. The Viking landers also carried their heavy descent rocket systems with them to the ground, which didn't matter because they stayed put. Curiosity would have had to lug all this unnecessary mass around Mars for years. The Opportunity rover, her sister ships Spirit and the earlier Mars Pathfinder, employed a combination of aerobraking, parachutes, rockets, and airbags to cushion the falling spacecraft. But these previous rovers were lightweight in comparison, at just over a fifth of the mass of the gargantuan Curiosity. A rover of this size and complexity bouncing over the surface in an airbag cocoon was not considered feasible, primarily because of the sheer mass of the airbag system needed to cushion the impact. The lightweight Opportunity rover's landing system was almost twice the mass of the rover itself. The chosen Entry, Descent and Landing Procedure, EDL, for Curiosity, was described by mission lead Adam Stelzner as the result of reasoned engineering thought. A beautiful example of the truism that reasoned engineering thought and common sense, at least of the sort possessed by the average golf club bore, do not always match up. The Curiosity EDL appears to the untrained eye to be bonkers, or maybe overcomplicated, but it wasn't, and it worked. Tucked up inside a protective shell, Curiosity encountered the outer layers of the Martian atmosphere, 125 kilometers above the surface and traveling at around 20,000 kilometers per hour, at 10:23 p.m. Pacific Daylight Time on the 5th of August 2012. The spacecraft, at this stage cocooned inside a protective enclosure, flew entirely under the control of its onboard computers, with no input from mission control on Earth. This was the first time an autonomous guided entry system was employed for an interplanetary mission, using a combination of thrusters and the ejection of balance masses to shift the center of mass and trajectory of the spaceship, and guide it with a design accuracy of around 10 kilometers towards the chosen landing site. This guided rather than ballistic trajectory allowed for a much wider choice of landing sites for Curiosity than for the previous landers, which required around 100 kilometers of flat, safe land surrounding the nominal touchdown point. But it also required the rover to fly itself. The round-trip travel time for a radio signal to Mars was over 13 minutes when Curiosity landed, making control from the Jet Propulsion Laboratory in California impossible. During the first stage of descent, a heat shield constructed from a unique material known as pica, phenolic-impregnated carbon ablator, protected Curiosity from peak temperatures of around 2,000 degrees Celsius, generated by friction in the thickening Martian atmosphere. 4 minutes after beginning the entry phase, slowed to just under 3,000 kilometers per hour, Curiosity's parachute deployed at an altitude of 11 kilometers above the surface. The supersonic parachute is a vast and complex structure, 80 suspension lines over 50 meters long, attached to a 16-meter canopy. Having slowed to a velocity of 700 kilometers per hour with the help of the parachute, the heat shield was jettisoned at an altitude of 8 kilometers, allowing the onboard radar to get a view of the ground and deliver high-precision altitude and velocity measurements. With the parachute fully unfolded in relatively dense, low-level Martian atmosphere, Curiosity drifted in the Martian sky for 80 seconds, descending ever more slowly. At an altitude of 1.8 kilometers, traveling at a sedate 280 kilometers per hour, the NASA timeline calls for a deep breath as Curiosity separated from the parachute system and dropped in freefall towards Mars. For engineers, says the NASA website, it's like jumping out of a plane for the first time. The freefall drop was designed to allow Curiosity to separate far enough from the parachute system so that it wouldn't accelerate back into it when 300 meters further down, its retro-rockets fired and the powered descent phase of the landing began. For the Viking landers, this was the final phase. But for Curiosity, after the rockets had delivered the rover to an altitude of just 20 meters with a descent velocity of less than 1 meter per second, almost a hover, the audacious final phase of the landing protocol kicked into action: the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an umbilical cord of electrical connections 7.5 meters in length. 4 of the rockets, angled away from the vertical so as not to damage the rover, continued to fire, allowing the whole delicate system to approach the surface at walking pace. At 5 meters from the surface, Curiosity unfurled its wheels, stowed for the 8-month journey from Earth. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface and issued one last command through the electrical umbilical up to the sky crane: "I'm down, cut the cables, and fly away." After a 500 million kilometer journey, Curiosity was delivered safely to Mars, just 2.4 kilometers from its nominal landing point. A triumph of engineering ingenuity and brilliance. Curiosity was sent to Mars to explore Gale Crater, a 150-kilometer wide impact crater formed during the late Noachian or early Hesperian period, when liquid water would have been present at least occasionally on the surface. In the great tradition of astronomy, the crater is named after the Australian amateur astronomer, planetary observer, comet hunter, and occasional banker, Walter Frederick Gale, who discovered a host of comets as well as a number of geological features on Mars at the turn of the 20th century, using self-built telescopes in his backyard. The primary reason for choosing Gale Crater was the unusual central structure Mount Sharp, or Aeolis Mons, which rises over 5 kilometers above the crater floor. There is still debate about precisely how Mount Sharp formed, but the layers visible from orbit along its flanks suggest that it is the weathered remains of sedimentary rocks which once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor once more, while leaving the towering central structure intact. Deep, exposed sedimentary layers are extremely enticing to geologists because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forwards through Martian time, and scientists are close behind. Joy Crisp, the deputy project scientist from NASA's Jet Propulsion Laboratory, explained the choice of landing site in the weeks before launch. Mount Sharp may be one of the thickest exposed sections of layered sedimentary rocks in the solar system. The rock record preserved in those layers holds stories that are billions of years old, stories about whether, when, and for how long Mars might have been habitable. Just as the layers of exposed rock in the Grand Canyon on Earth reveal the story of our planet, the exposed sedimentary layers of Mount Sharp are a storybook that the winds of Mars have opened, ready for Curiosity to read. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp, stopping along the way at each interesting site to characterise the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysis of the Martian surface and the layers just beneath. NASA loves acronyms. Curiosity acquires samples using the SSS, the Surface Sampling and Science System. It is made up of 3 parts: the SASPAR, Sample Acquisition, Processing and Handling Subsystem, SAM, Sample Analysis at Mars Instrument, and CHEMIN, Chemistry and Mineralogy Instrument. The main components of SASPAR, which is mounted at the end of Curiosity's robot arm, are an integrated scoop and sample processing system, Chimera, and a drill for acquiring surface and subsurface samples. The Scoop and Sample Processing System surely has one of the most inventive of all NASA acronyms. CHIMRA, pronounced Chimera, after the multi-headed creature of Greek mythology, which stands for the Collection and Handling for In Situ Martian Rock Analysis Tool. Someone deserves an award for that. These are transferred into SAM, which includes a gas chromatograph, a mass spectrometer, and a tunable laser spectrometer, and CHEMIN, the first X-ray diffraction experiment ever flown in space, and the most sophisticated modern technique for characterizing mineral samples on Earth. The science returned from Curiosity is only just beginning, as older data are analyzed and published, and new data from its climb up the slopes of Mount Sharp and through Martian geological time continues. But current results are consistent with, and greatly enhance the detail of, our picture of a planet that was warmer and wetter when Gale formed around 3.5 billion years ago. In early October 2012, Curiosity rolled to a halt at a place the geologists christened Rock Nest, and scooped up a handful of Mars. The sample of dust, dirt, and finely grained soil was fed into the SAM and heated to 835 degrees Celsius. The baking process revealed the presence of significant amounts of carbon dioxide, oxygen, and sulfur compounds. SAM's analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rocknest didn't just provide circumstantial evidence for ancient water. Around 3% of the sample's mass was water, suspended as small ephemeral droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A transient landscape of ancient streams, deltas and ponds is bounded by the border of the crater. When alighting on ancient riverbeds running down from the crater's rim, Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus and carbon, all the necessary building blocks for life. Summarizing the results in August 2017, Michael Mayer, NASA's lead scientist for the Mars exploration program, said, "A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes." In June 2018, two new discoveries strongly reinforced the idea that Mars was once a habitable world, and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface, in rocks known as mudstone that form from silt deposited on lake beds. This means that all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more tantalizingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today, reaffirming and enhancing previous observations of methane spikes from orbit. The important additional information from Curiosity was that the methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not irrefutable evidence of life on Mars today by any means. It's thought that geological processes may be able to account for such a seasonal variation, although if this were Earth, a biological explanation would be favoured. The appropriately cautious Michael Mayer had this to say in June 2018. "Are there signs of life on Mars? We don't know. But these results tell us we are on the right track." Science is a humble and cautious pursuit, and from the time of Viking we've known that Martian soil chemistry is notoriously complex and can easily catch out the unwary scientist. So we should leave it there. Curiosity continues its journey through Martian geological history emboldened. It is certainly driving across an ancient lake bed where, for a reasonably extended period over 3 billion years ago, conditions were favourable and all the ingredients for life were present. While we shouldn't speculate or read too much into the results to date, we can let our imaginations wander for a moment to picture what Gale Crater might have been like during the late Noachian, when life was gaining a foothold on her sister world. We stand on the shores of a lake partially filling Gale, fed by runoff from snowmelt on the far northern rim. Where Mount Sharp now stands, a small island breaks the surface blue, not the mountain of today, but a small central peak left over from the impact. A place of grand beauty, where each Martian evening the pale sun sets in the west beyond the island, rays glinting dimly off the still waters, interrupted by the shadow of the peak out to the crater's edge. A sundial, marking the passing of time, on a lake populated by microbial Martians. The crater counting techniques developed from our exploration of the Moon allow us to place our observations of Mars today in historical context. They allow us to construct an absolute timeline. If we see evidence that water once flowed across a surface or pooled within a crater, and we can date the area using crater counting, then we can estimate when the water flowed and when it disappeared. As we've discussed, Curiosity is exploring Gale and painting a vivid picture of what happened there. Crater counting allows for an estimate of when, independent from the rover's ground-based measurements. A recent analysis using images from orbit taken by MRO found 375 craters ranging in size from 88 meters to 23 kilometers inside Gale crater, implying an age of 3.61 billion years, with an uncertainty of around 60 million years. This places the formation of the crater and the geological events that played out inside it during the late Noachian, early Hesperian, and this time frame is consistent with observations of the presence of water at many other sites of a similar age. Consistency over a wide range of independent observations is extremely important in science. One site or set of observations alone may be tantalizing, but rarely compelling. Multiple independent observations reduce the uncertainty and give scientists more confidence in their understanding. When our goal is to understand the sequence of events on an ancient landscape far away that no human has ever visited, caution and consistency are both vital commodities. Since we have only one active rover at present, and landings are by their nature rare and confined to limited geographical regions, orbital observations of much wider areas of the planet are a vital tool. MRO's HiRISE camera has provided some of the most beautiful and detailed high-resolution photographs in the history of space exploration, covering over 99% of the Martian surface. Features as small as a meter wide can be seen in these images, and the camera can also operate in the infrared, allowing for the identification of different minerals at the surface. There are many beautiful photographs in the MRO library that reveal evidence of persistent lakes and river systems, particularly across the Noachian terrain in the southern highlands. Sites such as the Jezero crater clearly show meandering river channels draining into deltas. Some images, constructed using both visible light and data from the spacecraft spectrometer, reveal well-defined river channels flowing out of the crater and the presence of carbonates and clays that form where there is persistent liquid water. For these reasons, the Jezero crater is one of the 3 prime targets for NASA's Mars 2020 rover. Some of the more recent finds are associated with the Arabia Terra region, which sits between the Noachian southern highlands and the great lowlands of the north, where water could have flowed towards a possible northern ocean. Researchers from University College London and the Open University studied an area of Arabia Terra equivalent to the size of Brazil, using high-resolution imagery from MRO. The study mapped a network of over 17,000 kilometers of ancient river channels, not the usual excavated dry river valleys, but rather a network of inverted channels, raised lines of sand and gravel laid down on the riverbeds that persisted while the land around them eroded away long after the rivers dried. Similar ghost rivers are seen in desert environments on Earth in Utah, Oman, and Egypt, where erosion rates are slow. The identification of the ghost rivers allows for Arabia Terra to be identified as a fossilized floodplain, somewhat like the lower sections of the river Ganges on Earth, the lowland interface between mountain rivers and the sea. This is an important discovery because it feeds into a long-standing and still unresolved scientific debate about the nature of the Noachian climate. Nobody disputes that rivers once flowed on Mars, or that many impact craters were once home to lakes. The key question is one of longevity. Was Mars warm and wet for long periods of time, or was it for the most part a frozen planet on which water occasionally melted, perhaps triggered by sporadic volcanic activity or shifts in the planet's orbit? The tension arises because climate modelers find it very difficult to simulate an ancient Martian atmosphere thick enough to deliver a stable climate over hundreds of millions of years that would have been lost at a sufficiently fast rate to produce the Mars we see today. In a recent review, for example, Robin Wordsworth concludes, "The weight of geochemical and geomorphological evidence points towards a late Noachian hydrological cycle that was intermittent, not permanently active. And the latest state-of-the-art Martian climate simulations suggest a water-limited early Mars with episodic melting episodes may be a suitable paradigm for much of the later Noachian and early Hesperian climate." Before the recent analysis of the Mars Global Surveyor data, It was thought that there was a relative absence of river channels on Arabia Terra, and this was interpreted as support for a frozen, episodically wet Mars. Ice may have been concentrated in the southern highlands, and so lower elevations like Arabia Terra may have been generally more arid and therefore devoid of river channels. This appears not to be the case. Arabia Terra was once very wet indeed. This debate has no consensus resolution at the time of writing, which reminds us of important points about both our knowledge of Mars and science in general. We are describing and attempting to understand and contextualize events that happened over 3.5 billion years ago, at or around the time that life on Earth began. That is an immense span of time, during which orbital parameters have changed, solar output has varied, and innumerable impact events have cratered the planets. Tracing the evolution of an atmosphere backwards through time from today's measurements, anchored by geological and geochemical evidence from a few landing sites and orbital imagery, is extremely difficult. Suffice to say, there remains an unresolved tension between Mars's small size and large distance from the Sun, and the clear evidence of an ancient water cycle, episodic or persistent. As Wordsworth writes in the introduction to his review, the nature of the early Martian climate is one of the major unanswered questions of planetary science. The complexity and apparent intractability of the mystery is reason enough for many scientists to study Mars. The character of the scientist requires not only comfort with, but attraction to the unknown, an acceptance of and delight in the complexity of nature. There is no simple story of any planet. They are each too big and too old and subject to too many variables. We might reflect on what that means for our own existence, as individuals and as a species. The specific fact of our existence is inextricably linked with the evolution of our planet through an incomprehensible web of cause and effect stretching back via major and minor events, many beyond Earth itself, and filtered by the multidimensional sieve of evolution by natural selection. This connects us with every living thing that went before, back to the origin of life almost 4 billion years ago, and the origin of our planet 500 million years before that, and the origin of the solar system and the laws of nature who knows when, perhaps during the Big Bang, or perhaps infinitely far away in time. There's a lot we can't know. The search for certainty is a fool's errand, and the lesson is to find delight in not knowing, while simultaneously committing to extending the domain of the known. That's the key to science, the key to happiness, and the only reasonable response to the existential challenge of existence, because it is the truth. If you don't like that, comfort yourself with the fact that the domain of the knowable is vast, possibly infinite, and perhaps paradoxically, the knowable things about Mars may exceed those about Earth. Because Mars has been in deep geological freeze for much of its life, it is easier to research the deep past than it is on Earth. And that deep past may include the origin of life. Traces of the geochemical alchemy that led to the emergence of self-replicating, information-carrying carbon molecules on Earth 4 billion years ago weathered away long ago, although clues may be found in the common structures and chemistry of living things today. On Mars, however, geochemistry was frozen and archived in regions such as Arabia Terra. If, therefore, life began or even still exists subsurface on Mars, such a discovery may deliver insight into our own origins that would simply not be possible by studying the weathered, ever-changing ecosystems of Earth. This may be the gift of unknowable Mars. She's less unknowable than Earth. The Eridania region of the southern highlands may provide the most compelling evidence yet of a warm, wet, early Mars, with conditions not dissimilar to Earth at the time when life began. The analysis we describe below is a beautiful example of how the suite of science instruments aboard multiple spacecraft in orbit around Mars can be combined with our knowledge of cratering rates on the Moon to characterize an environment and trace its history back through deep time. It is also a beautiful example of the interconnected nature of science and the value of exploration. We've already met the elevation maps from the Mola aboard the Mars Global Surveyor. This topological data, in concert with visual data from MRO revealing the location of valley networks, suggests that the Eridania Basin was once a giant lake, possibly the largest ever to exist on Mars, 1.5 kilometers deep in places, and containing 3 times more water by volume than the Caspian Sea on Earth. We know the terrain is late Noachian, around 3.7 billion years old, from crater counting. The CRISM spectrometer on board MRO reveals the mineralogical composition of different areas of the Eridania Basin, and this can be used in conjunction with the topological and visual data to build a 3-dimensional picture of the landscape and its chemical composition. In the deepest areas of the Eridania Basin, magnesium and iron-rich clay minerals are common, laid down as sheets of saponite, talc, serpentine, and so-called tot clays. These are characteristic of seafloor environments on Earth. Materials known as iron-rich phyllosilicates are also seen, which are again characteristic of terrestrial seafloor deposits. The mineral jarosite is detected, suggestive of the chemical weathering of sulfite deposits. There are many different carbonate signatures containing iron, manganese, magnesium, and calcium. Higher up the basin walls, chlorides are found, which are indicative of evaporation in shallower water. The most likely explanation for the origin of the deep clay, carbonate, and sulfite deposits, it's argued, is volcanic activity on the floor of a deep lake, because very similar deposits are seen at hydrothermal sites on Earth. The iron minerals detected are similar to those formed in the iron-rich early oceans of Earth, prior to the release of large amounts of oxygen into our atmosphere by photosynthesis. All this beautiful topological, visual, geophysical, and geochemical data can be combined to produce a picture of what was happening in the Eridania Basin around 3.7 billion years ago. The geochemistry of the low-lying regions is indicative of a deep-sea, volcanically active hydrothermal environment, with the salt-rich deposits at higher elevations suggestive of slow evaporation in shallower waters. The basin contained an iron and mineral-rich ocean, energized by active volcanism deep below the waves. A cauldron of complex geochemistry, stirred by the constant flow of energy from the inner planet. This is a striking conclusion because at the same time, a few 100 million kilometers across the solar system on Earth, many biologists believe that life began in similar deep-sea volcanic environments. The theory that life on Earth began in hydrothermal vent systems is mainstream, although not universally accepted by any means. The idea is partly based on the observation that all living organisms on Earth today share a chemistry associated with the establishment of gradients in the concentration of protons across membranes, known as chemiosmosis. Proton gradients are also characteristic of the geochemistry of alkaline hydrothermal vent systems in acid oceans, which were common on the young Earth and perhaps the young Mars. An analysis published in 2017 claims to have detected evidence of biological activity in rocks laid down by hydrothermal activity at least 3.77 billion years ago in the Nouveau-Guitook crustal belt in Quebec, near the Greenland Ishua rocks. The evidence comes from tube-like coils of the iron oxide mineral hematite, similar in size and form to structures laid down by iron-oxidizing bacteria in hydrothermal environments today. It's possible that the rocks at Nouveau-Guitook are much older. A radiometric date using the samarium-neodymium decay process suggests an age of 4.28 billion years, which would make them by far the oldest rocks on Earth, and an astonishingly early date for biological activity. These findings are controversial, in part because of the difficulty of understanding how Earth's active geology has modified the samples over such vast timescales. This is where Mars may have an advantage over Earth in helping us to understand the processes by which the chemistry of a planet became the chemistry of life. The environment at Eridania is far better preserved than that at Nouveau-Aghitouk. It has been in sterile, almost deep freeze conditions for over 3 billion years, the ultimate laboratory for studying the origin of life, if indeed life began on Mars. The story of the Eridania Basin and the possible scientific promise it holds was pieced together by using the results from different instruments on different spacecraft over many years, spanning several scientific disciplines: geology, chemistry, spectroscopy, laser altitude ranging, and photography. The estimate of the age of the surface required the Apollo lunar rock samples from 50 years ago, and radiometric dating techniques which required an understanding of nuclear physics. The estimate of the age of the surface requires a model of the entire solar system in order to interpret the measured crater density, which illustrates another important idea. The solar system is a system. No planet is an island. No planet can be understood in isolation, just as the structure of any one living thing on Earth cannot be understood in isolation. Organisms are a product of evolution by natural selection, the interaction of the expression of genetic mutations and mixing with other organisms in the ecosystem and the wider environment. The planets formed in a chaotic maelstrom from motions as random as the impact of a cosmic ray on a strand of primordial DNA. And whatever worlds emerged from the chaos have had their histories shaped profoundly by their mutual interactions throughout their evolution. The late heavy bombardment is a beautiful example. If indeed we discover that life began in the Eridania Basin, what a magnificent illustration of the unity of knowledge that would be. Understanding developed over centuries, the life's work of thousands of explorers, field geologists, chemists, biologists, astronauts, engineers, distilled into the discovery of a second Genesis. But more than that, because of the pristine nature of the ancient environments on Mars, such a discovery would deliver an insight into our own origins that may not be available to us here on Earth. Mars is a time capsule, containing the frozen chemistry of an ancient world similar to the Earth when life began. But while Earth's deep past has been largely erased by 4 billion years of geology and the action of a complex global living ecosystem, which has transformed the planet and its atmosphere beyond all recognition, Mars is a fossil from the deep past. This raises the wonderful possibility that another world, albeit an integral part of our system, may be the key to decoding the mystery of the origin of life here, the reason we exist. It's almost as if we have to leave the cradle in order to truly understand it. Around 3.5 billion years ago, change was underway on Mars. The warmer, wetter episodes that characterized the planet for millions of years during the Noachian became less frequent, and the climate drifted, imperceptibly at first, towards the colder, arid state we recognize today. The water that flowed freely over the surface during the Noachian became locked away in giant reservoirs of ice. Lakes turned solid, and rivers ran dry. The planet wasn't dying, far from it. The fireworks of the late heavy bombardment had faded, but rumbles from the deep maintained the violence. The shield volcanoes of Tharsis, including the mighty Olympus Mons, continued to build even as global temperatures plummeted, and subsurface lava flows occasionally melted the reservoirs of ice, leading to catastrophic floods that challenged the imagination in their scale and violence. The age of Noah became the Hesperian, the age of floods, or rather less portentously and more accurately, the age of occasional floods. The Hesperian period is named after the Hesperia Planum, a giant lava field to the northeast of the Hellas Basin in the southern highlands. The plain was resurfaced partly by the volcano at its center, Tyrrhenus Mons, and spans almost 2 million square kilometers. First photographed by Mariner 9 in 1972, it's a relatively flat landscape with few visible rock formations. The most prominent surface features are the craters that allow us to date it. Tyrrhenus Mons is a very different volcano to Olympus Mons and the giants of Tharsis. It's much more ancient, fully formed not long after the Hellas impact 4 billion years ago, and it erupted through water or frozen ground, a process that produces large amounts of ash rather than lava, what geologists call a pyroclastic eruption. As a result of its age and composition, Tyrrhenus was more prone to erosion than the giants of Tharsis, and today stands only 1.8 kilometers above Hesperia Planum. The Hesperian period was coincident with increased volcanic activity, particularly at Tharsis. But there's not necessarily a causal link between volcanic activity and the transition from the Noachian to the Hesperian. What is clear is that volcanism became the dominant geological force on Mars as the long-lived water cycles waned and cratering rates declined after the late heavy bombardment around 3.5 billion years ago. This is seen in both surface features and mineralogy. Hesperian surfaces are richer in sulfates rather than the clays and carbonates of the Noachian. Sulfates form in the more acidic atmospheric conditions created by the release of sulfur dioxide from volcanoes. While volcanic activity was the dominant force sculpting the smoother Hesperian landscapes, there are spectacular and notable exceptions where water reasserted its dominance, if only for a moment. Ekus Chasma is an unremarkable valley today. Images taken by MRO reveal a deep, steep-sided depression lying to the north of the Marana Valley. At 100 kilometers long, 10 kilometers wide, and between 1 and 4 kilometers deep, it would be impressive on Earth, but is dwarfed by the magnificent neighboring valley system. 3.5 billion years ago, on frozen Hesperian Mars, however, things were different. High above, on the Tharsis Rise, lava surged upwards through the crust and met great reservoirs of ancient ice, releasing vast amounts of water that raged down from the southern highlands. The meltwater was funneled towards Ekus Chasma, where it created one of the briefest and yet most spectacular wonders of the solar system. The waters from the highlands came tumbling over the cliffs, roaring 4 kilometers down into the valley below, over the largest known waterfall in the history of the solar system. Around 350,000 cubic kilometers of water cascaded through the valley, the equivalent of a cube 70 by 70 by 70 kilometers, in less than 2 weeks. This being Hesperian Mars, the atmosphere was not substantial enough for the liquid to persist on the surface, and the water disappeared as quickly as it came, leaving scant evidence of the great falls etched into the canyon walls. Ekus Chasma was unique in scale, but the cycle of volcanic eruption followed by fleeting catastrophic floods was repeated in many locations across the planet throughout the Hesperian. However, in the thinning atmosphere, the presence of liquid water was probably always fleeting, increasingly so as time passed. Hesperian became Amazonian around 3 billion years ago, plus or minus 500 million years or so. When a Mars expert is asked the question, when did the Amazonian begin, they will usually say, depends who you ask. But certainly by 2 billion years ago, long before there was complex multicellular life on Earth, Mars was pretty much indistinguishable from the planet we see today. The red planet didn't die entirely. Volcanic eruptions persisted and have occurred in the very recent past at Tharsis. There may yet be eruptions in the future. But we do know that Mars changed from a world that supported liquid water on the surface under a thick atmosphere, via a period dominated by intense volcanic activity and episodic floods, into a hyper-arid frozen planet with a tenuous atmosphere, more befitting its small size and place in the solar system. This drama played out very roughly during the first 1.5 billion years of its life. The challenge is to understand why. The climate of a rocky planet is a complex dynamic system shaped by myriad interactions, feedbacks, and instabilities, and inevitably changes over geological timescales. The thin envelope of atmospheric gases can be affected dramatically by volcanic and tectonic activity and impacts from space, and on longer timescales by shifts in orbit and tilt, and changes in solar output. Earth seems to be a remarkable exception. The most dramatic atmospheric change over the last 3 billion years has been the gentle introduction of oxygen by photosynthesis. Mars today has a thin atmosphere composed primarily of carbon dioxide. We know this atmosphere must have been significantly thicker in the past, quite possibly at an even higher pressure than that of modern-day Earth, because there was once liquid water on the surface. Mars must therefore have lost most of its original atmosphere, and it's important to understand where it went and why. The ancient atmospheric carbon dioxide molecules could have frozen out onto the surface in the polar ice caps, become locked away in the subsurface as carbonate minerals, or they could have been lost to space, or some combination of all three. To measure the composition of the Martian atmosphere today and understand how it evolved over time, a dedicated mission arrived in orbit in September 2014. MAVEN, the Mars Atmosphere and Volatile Evolution mission, has no high-definition cameras and provides no dramatic photographs of the surface, because the questions MAVEN was designed to answer are about the invisible envelope of gases surrounding the planet. If curiosity is the extension of our hands and MRO our eyes, MAVEN is our nose, sniffing the air for clues to the past. The spacecraft operates in a highly elliptical orbit, bringing it as close as 150 kilometers above the surface and out beyond 6,000 kilometers. This eccentric path means that on every orbit, MAVEN experiences a wide profile of the Martian upper atmosphere, allowing it to build a three-dimensional picture of the gases that still remain and how their distribution changes with altitude and time. MAVEN's measurements show that Mars is losing atmospheric gases today at a rate of about 2 kilograms a second. The question is, how is the atmosphere being lost, and where is it going? The MAVEN team carried out an ingenious analysis based on observations of the concentrations of two different isotopes of the noble gas argon, argon-36 and argon-38. Argon-38 is chemically identical to argon-36, but it's heavier because it has two additional neutrons inside its nucleus. The ratio of argon-38 to argon-36 is sensitive to the rate at which the atmosphere is being lost to space through a process known as sputtering. High-speed electrically charged particles from the solar wind hit atoms in the upper atmosphere and literally knock them out into space. Because argon-36 is lighter than argon-38, the relative abundance of argon-36 in the upper atmosphere is enhanced. In technical terminology, argon-36 has a larger scale height than argon-38. This means that argon-36 is preferentially lost to space through sputtering, and the ratio of argon-38 to argon-36 increases. Since there's no other way that argon can be removed from the atmosphere, it doesn't react with anything, and it doesn't freeze at anywhere near the temperatures seen on Mars, the argon measurements provide a very clean indication of the way the Martian atmosphere is affected by the solar wind. By using measurements from MAVEN at different altitudes during its elliptical orbit, and surface measurements of the argon isotope ratio from Curiosity, this beautifully elegant experiment enabled the team to determine that 66% of the argon in the Martian atmosphere has been lost over the planet's 4.5 billion year lifetime. Once this rate of argon loss has been determined, the rate of other atmospheric components can be calculated. The published results concluded: the evidence from MAVEN observations suggests that a large fraction of the Martian volatile inventory has been removed to space, and that loss to space has been an important process in the evolution of the Martian atmosphere through time. In particular, a large fraction of the dominant component of the Martian atmosphere, the powerful greenhouse gas carbon dioxide, has been lost to space through the interaction with the solar wind, with a smaller fraction being locked away in subsurface carbonate deposits, and an even smaller fraction stored as frozen carbon dioxide in the polar ice caps. These changes, the authors conclude, appear to be large enough to account for the change in the Martian climate inferred from the planet's geomorphology. Without declining levels of greenhouse gases in the atmosphere to keep in warmth and protect its lakes and oceans, Mars was destined to become a frozen desert world. But why has Earth not suffered the same fate? We are, after all, closer to the Sun and bathed in a more violent solar wind. Why has our atmosphere survived the solar onslaught for several billion years after the Martian atmosphere was stripped away? The solar system is in fact a system. Although we might feel isolated on a ball of rock in the dark, that is an illusion. No planet is an island. The system evolves as one. Draw a diagram of the food chain underpinning all complex life on Earth today, and at the base is a stream of photons generated 150 million kilometers away inside the Sun. Green plants are the interface between a star and civilization. Our understanding of Mars demonstrates that a planet's relationship with the Sun is not all light and sweetness. The star can provide the energy for life, but the solar wind can also destroy life or prevent it from ever emerging through the damage it can cause to planetary atmospheres. The solar wind emerges from the Sun's atmosphere, known as the corona. The temperature at the Sun's surface is 6,000 degrees Celsius, but the temperature of the corona is over 1,000,000 degrees Celsius, heated by energy transferred from the surface by the powerful solar magnetic field, twisted and coiled by the star's rotation. At such high temperatures, atoms cannot hold together. Electrons are ripped away from atomic nuclei, and matter exists in a fourth state, not solid, liquid, or gas, but a soup of negatively charged electrons and positive ions known as a plasma. Some of these particles are moving so fast that they escape the Sun's embrace completely, streaming outwards across the solar system at velocities in excess of 800 kilometers per second. This is the solar wind. When these high-energy charged particles reach Earth, most do not smash directly into atoms at the top of our atmosphere, because we are protected by our magnetic field. They are deflected harmlessly by stretching and distorting the field out on the night side of the planet. The stretched field occasionally reconfigures, accelerating electrically charged particles back down the magnetic field lines to the Earth's poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. This is the aurora, the northern and southern lights. From Earth, the aurora can be seen by those lucky enough to be far enough north or south on the right night, when the sky is clear, the Sun is active, and the interplanetary magnetic fields are favorably aligned. From the lofty vantage point of the International Space Station, the aurora reveals itself as halos dancing around the poles. It is an unforgettable sight, undoubtedly one of nature's wonders. But as is often the case in science, and in life for that matter, the experience is greatly enhanced by knowledge. The lights, dancing faster than the eye can see, or perhaps the brain can comprehend, are a direct result of the structure of atoms. Electrons shifting between allowed energy levels, determined by the number of protons in the atomic nucleus that holds them captive. High-altitude oxygen glows red. An atom is struck by a charged particle accelerated down the Earth's magnetic field lines towards the pole. The interaction shifts an electron into a long-lived, excited configuration. If the atom is not involved in a collision in the thin air for around 100 seconds, an eternity in atomic time, the electron will shift down closer to the nucleus, and a red photon will be emitted. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. This time the atom must avoid collision for around a second, still an atomic eternity in the denser air. Excited nitrogen molecules add a deep red or pink to the lower edges of the towering curtains of light during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. To calculate the colors, physicists treat the electrons as waves trapped inside a deep well created by the electric charge of the protons. Particles imagined not as tiny flecks of matter, but as fields that can span great volumes of space. The energy to drive the display comes from nuclear fusion reactions inside the Sun. a factory 1,000,000 times the volume of Earth, converting hydrogen into helium at a rate of 600 million tons per second. The weak nuclear force acts slowly and grudgingly to convert protons into neutrons in the core. Nuclear alchemy that results in the creation of neutrinos, which stream across 150 million kilometers at close to the speed of light before passing unhindered through the entire planet on their journey to infinity. Thus, 60 billion per square centimeter stream through your head every second without even a nudge, because your head is almost entirely empty space, and neutrinos hardly ever come close enough to interact with your sparsely distributed molecules. It might happen once in your lifetime. The nuclear forces at work inside the Sun also assembled the heavy elements that make up your body inside old stars long ago from hydrogen and helium forged in the first few seconds after the Big Bang. Carbon, oxygen, nitrogen, sulfur, phosphorus, and iron. Gravity assembled the stars by forcing the collapse of primordial interstellar clouds, causing them to heat up in their centers and triggering the nuclear reactions that release the energy to halt the collapse for a few billion years, long enough for life to emerge in the gradient between the nuclear furnaces and the chill of the expanding universe. All of these thoughts are ignited in the imagination by the auroral display. Our experience is enhanced by knowledge. A central component of the web of physical processes that make the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet and allows it to return in a much subdued form to the poles. Without this, the processes that Maven observes stripping the atmosphere of Mars would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo, which is easy to explain in broad brush terms, but extremely complex and not fully understood in detail. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle, and the Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other subtleties. The rate of heat flow through the mantle is affected by geological processes including plate tectonics and volcanism. The precise nature of the flows depends on the constituents of the core other than iron, for example the sulfur content and distribution, and so on. It's fiendishly complicated, and because of this complexity, our planetary magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo, because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands, suggesting that these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. The Martian meteorite ALH 84001, dated at 4.1 billion years old, also shows clear signs of having formed in the presence of a magnetic field. These observations lead to the current baseline view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onwards, the atmosphere was exposed to the full force of the solar wind, and the Maven results tell us that this was likely the key driver for the loss of the Martian atmosphere. It would be tempting, but wrong, to suggest that the loss of the magnetic field was the trigger that drove the change from the Noachian to the Hesperian. The timescales probably don't match, and in any case the loss of the magnetic field wouldn't have led to an immediate loss of the atmosphere. Sputtering is a gradual process which still continues today. There have been speculative attempts to link the switch-off of the dynamo to the Hellas impact, or multiple impacts around the time of the late heavy bombardment. The idea is that the heating of the mantle can disrupt the heat flow out from the core, in turn disrupting the smooth convective flows. At the time of writing, the sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years in response to gravitational interactions with the other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle, and even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice tilted towards the Sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more tenuously than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind, and the surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by ESA's Mars Express spacecraft. Blue ghosts of a Martian past generated by localized magnetic hotspots scattered across the planet, and the last traces of carbon dioxide in the atmosphere, energized by the relentless solar winds. Despite its 3 billion-year quiescence, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbor a solar system's lifetime away. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence for Martians within the next decade. The discovery of a second Genesis would have important philosophical, scientific, and cultural consequences. It would mean that, given the right conditions, liquid water, active geology, and a sprinkling of organics, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat and minerals and gas. We are bubbling chemistry that thinks. If it happened on 2 neighboring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not God's children, but we are also not alone. Of even greater importance, I think, is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface, and a great wealth of mineral resources, all the things that are necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. The message from Mariner 4 was not interpreted correctly. There is a second chance for us on Mars when we feel ready to take it. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. The Earth is by far and away the best planet we know of anywhere in the universe. We were born of it and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the new world, living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there? The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. In Werner Herzog's film Encounters at the End of the World, a man named William Gierser describes the sort of person who gravitates to Antarctica, the last of Earth's frontiers. I like to say, if you take everybody who's not tied down, they all sort of fall down to the bottom of the planet. So that's how we got here, you know? We're all at loose ends, and here we are together. I remember when I first got down here, I sort of enjoyed the sensation of recognizing people with my travel markings. I was like, hey, these are my people. PhDs washing dishes and linguists on a continent with no languages. Mars is the step beyond the Antarctic, and perhaps we all need to take it in our imaginations. Our civilization feels untethered to me. We're at a loose end, huddled in a tiny corner of our system. We watch the wandering planets and the wheeling stars and the cycles of day and night, and wonder what the hell we're doing. We're all linguists on a continent with no languages. As a consequence, we scrabble around, eking out the ever more precious resources on Earth, trying to expand and build more stuff and grow in a thin shell of air on the two-dimensional surface of a small rock, giving little thought for the three-dimensional path marked by the lights in the night. Robert Zubrin, the visionary engineer whose work has inspired, amongst others, Elon Musk, likes to say that ideas have consequences, and the worst idea in the history of humanity is that we must compete for limited resources. This is false. The solar system contains raw materials beyond our needs or desires, and they will become resources when we choose to access them. The international tensions created by the competition for earthbound resources are based on the entirely false and dangerous idea that resources are limited. False, false, false. We have the technology, and perhaps as we drift ever more aimlessly, we may discover the will to unlock the unlimited treasures in the vast solar system of which we are a part. We need to shift our collective consciousness. We burn too bright for this world alone, but that does not mean we should extinguish the flame. We must forge a new path that transcends competition between nations, that requires the wholesale rejection of the mindset that mistakenly compels us to retreat or fight over dwindling resources on a single groaning planet. We must transform ourselves into a multi-planetary spacefaring civilization, and this begins with the colonization of Mars, an achievable goal forged from the human desire to explore and expand without pushing up against someone else's border fence or damaging our planet beyond repair. Imagine the magnificent intellectual and physical vistas, the new technologies, the opportunities, the excitement of creating a new society. The joy of extending our collective experience and hopes and dreams to a new world and worlds beyond. Mars has a pivotal role to play in our future. If we don't go there, we'll never go anywhere. And if we go nowhere, we'll die here. Breathing new life into the old red planet will breathe new life into us. It will be our first step beyond the cradle and onwards to the stars. Earth before life, 4.5 billion years ago, was no nascent Eden. closer to the realm of Hades than the Garden of God. Molten and smouldering, cloaked in toxic clouds through which the young sun could barely break to signal the coming dawn. The planet still trembled from the aftermath of a glancing collision with Mars-sized Theia, now fragmented into a ring of debris that, given time, coalesced with the ejected rubble of Earth to form the Moon. 4 billion years later, two people who owed their existence to the energetic geology of Hadean Earth stepped onto the surface of the coalesced rubble and considered their position in the firmament. From their vantage point, Armstrong and Aldrin viewed a peaceful, pristine planet that has been many different worlds since its formation. How do we know? How can we speak with any authority of events that happened billions of years ago, beyond not only memory, but also life on Earth itself? How is such a timeline calibrated? The answer lies in the rocks. Apollo delivered many treasures, countless engineering breakthroughs, a generation inspired, Earthrise from Apollo 8, the simple joy of exploration. But scientifically speaking, the treasure was rock. 382 kilograms of rock collected from 6 landing sites. On the Moon, as on Earth, rocks can be dated with great accuracy, using the natural clocks provided by the radioactive decay of certain atoms. The chemical element rubidium, for example, occurs naturally and quite commonly in a form known as rubidium-87, which is found in many potassium-rich minerals. It is unstable, with a half-life of 48 billion years. This means that over a period of 48 billion years, half of the rubidium-87 atoms that were present in a rock when it formed will have decayed away, transmuting into another sort of atom, strontium-87. An older rock will have fewer rubidium-87 atoms and more strontium-87 atoms. There is a little more to it than that, of course. How do we know how many rubidium and strontium atoms were present when the rock formed? The clever part of the dating procedure is that we don't need to know. The method, called the isochron method, relies on the fact that there is another naturally occurring form of strontium, which is not produced by radioactive decay, known as strontium-86. Strontium-86 is stable and chemically identical to strontium-87. The only difference is that it has one more neutron inside its nucleus. This means that any strontium-86 atoms inside a rock today were present when the rock originally formed. By counting the number of rubidium-87, strontium-87 and strontium-86 atoms in a selection of samples taken from a rock, it is possible to calculate the absolute time elapsed since the rock formed. On Earth, some of the oldest crustal rocks are found off the southwest coast of Greenland at a place called Ishwa. Using rubidium-strontium dating, we know these rocks were formed 3.66 billion years ago, with an uncertainty of 0.06 billion years. The oldest known rock on Earth was found in Jack Hills, Western Australia. It formed 4.404 billion years ago, with an uncertainty of 0.008 billion years. All known samples from Earth's crust are younger than 4 billion years old, because the seething surface of the Hadean Earth meant that rocks were constantly being melted and reformed, resetting the radiometric clocks. The same analysis can be carried out on meteorites that have fallen to the surface of Earth from space. The majority, over 1,000 known, formed between 4.4 and 4.6 billion years ago, which is consistent with independent estimates for the age of the solar system, using, for example, helioseismology measurements of the amount of helium in the Sun's core. The youngest of the moon rocks returned by the Apollo astronauts were 3.2 billion years old, and the oldest were 4.5 billion years old. 12 of the samples were over 4.2 billion years old. The variation in age of the moon rocks at the Apollo landing site is extremely interesting and important, and it forms the basis of the most accurate technique for dating areas of the Moon from which we have no rock samples. We can make a graph showing the age of the rocks collected from each Apollo landing site and also the Russian Luna 24 robotic sample return mission, plotted against the number of craters per square kilometre at the site. The dark blobs around the labels of the various missions will represent the uncertainty of the measurements of the ages of the rocks and the crater counts. Two very low and uncertain points from the craters Copernicus and Tycho are from rocks collected by Apollo that are thought to have been thrown into the landing sites by the impacts that created these two distinctive lunar craters in the much more recent past. Two solid lines curve up across the plot, bounding the measured points. Older sites have more craters, which is easy to understand because there's been more time for meteorite impacts to build up. Surfaces that were created in the more recent past, such as the Copernicus crater, have experienced many fewer subsequent impacts. Imagine now that there's an area of the Moon from which we have no samples, but we do have photographs of that location from space. We count the number of craters per square kilometre. Let's say we get an average of 0.0002 craters above a diameter of 4 kilometres per square kilometre. This allows us to say that the surface formed somewhere between around 3.2 and 4 billion years ago, similar in age to the Apollo 17 landing site. This is one of the simplest uses of the graph. More importantly for our purposes, we can extrapolate the graph from the Moon to Mars. We have to make some model-dependent estimates of how the number of impacts changes because Mars is a larger planet with a stronger gravitational pull, and to account for Mars's different place in the solar system closer to the asteroid belt, the source of most of the impacting objects. We can do this with some confidence, and this is the primary way we estimate the absolute age of the different regions of Mars. The Noachian terrain is the oldest and has the highest density of craters, followed by the Hesperian and the Amazonian. The northern lowlands have been resurfaced by volcanic activity in the more recent past, which we know because they're relatively devoid of craters, much like the lunar seas. In this way, the absolute dates we quote for events on Mars are all ultimately tied to the radioactive dating of moon rocks. And this is one of the main reasons why the Apollo rock samples from different landing sites are so valuable scientifically. There's another key line on the graph, a dashed line we'll call constant production rate. The number of craters plotted against age would follow this line if the Moon had been subjected to a constant rate of impacts throughout its history. The measurements follow this line until we get to the surfaces around 3.8 to 4 billion years old, when the number of craters increases dramatically, implying that in the early history of the solar system, there was a time when the rate of impacts was much greater than today. That's not surprising. We might expect that the young solar system would have been filled with leftover rubble from the formation of planets, and so a more violent place. But there is a complication. If we assume that the impact rates seen on the oldest lunar terrains, such as the Apollo 16 landing site in the Descartes Highlands, were sustained all the way back to the Moon's formation, then the impact rate would have been impossibly high. The amount of mass falling on the surface of the Moon would have been similar to the mass of the Moon itself. We know that didn't happen, so the assumption is that the rise of the impact rate curve on the graph is in fact a spike that peaked around 3.9 billion years ago, and then returned to the much lower impact rate from earlier times. This violent spike in the rate of impacts from space is known as the late heavy bombardment. The cause of the late heavy bombardment is not known, but a leading theory is that Neptune changed its orbit from inside to outside that of Uranus, and the resulting gravitational disturbance deflected a maelstrom of icy objects in the distant Kuiper belt towards the planets of the inner solar system. We might reflect on the interconnected nature of knowledge and of the solar system. Exploration of the Moon provided us with the intellectual tools to date the surface of Mars, using the scars delivered by objects deflected into the inner solar system by events that occurred far away in space and time, beyond the orbit of either world. It's a story that began before the solar system even truly existed. 5 billion years ago, a vast interstellar cloud of dust and gas, at least 65 light-years across, that's 6.1 times 10 to the power of 14 in kilometers, began to collapse and coalesce under its own enormous weight. Fragmenting into a collection of smaller, dense cores, one of these gigantic clumps formed what is known as the pre-solar nebula, the embryo from which every part of our solar system would develop. In this dense cloud of gas comprised almost entirely of hydrogen and helium, hung every atom that would go on to form the sun, the planets, and every element that would define the character of each of these worlds, including the ingredients of life, the components of you and me. What triggered this cloud beyond the tipping point and on to the next stage of its stellar evolution is lost in the eons of time. But astonishingly, we have been able to pull together scraps of evidence to guide us. By studying some of the oldest meteorites ever discovered on the surface of the Earth, we've been able to get a glimpse of the time when it all began. Locked away inside these ancient meteorites are the unmistakable signatures of rare forms of iron that we believe can only have been created under a very specific set of conditions. The only place in the universe where these rare isotopes can be formed is at the heart of giant, short-lived stars at the very moment they explode. In other words, they are the product of supernovae. This clear chemical fingerprint from rocks dating back to the earliest days of the solar system, over 4.5 billion years ago, suggests that our solar system emerged among a cluster of thousands of stars in a large stellar nursery, perhaps not unlike the Orion Nebula, the star-forming region that lies closest to the Earth at 1,500 light-years away, which can even be spotted with the naked eye in the night sky.